Let's talk about something that's not necessarily a secret, but treated as one. It also happens to be kind of my passion. One of the toughest topics in Java is how the JVM deals with the memory. This course helps you to truly understand the Java memory and garbage collection process. We'll zoom in on the phases of garbage collection, the various implementations of the garbage collector, and we'll also zoom in on the different parts of the heap. We'll also dive into the non-heap space. After that, we'll talk about tuning the JVM for a bit. You'll learn how to adjust the heap size and meta space and how to modify the options for the garbage collector. We'll end this course with a situation that we preferably want to avoid, or at least spot as early as possible. Before we get started with this next step in memory management, let's first make sure that this is the course for you. In order to be able to follow along, you'll have to know the basics of memory management in Java. If you're not familiar with the memory management yet, please check out the first part of this series, Java Memory Management, Values and References. If you already have the basics of memory management down, then let's get moving. So we have the stack memory and the heap memory in Java. On the stack, we store primitive values and references to objects. On the heap, we store the actual objects. These objects on the heap, they contain primitive values and references to other objects on the heap. The stack memory gets cleaned up automatically. Whenever a certain method is done executing, the values and variables for this method are forgotten, since there is no way back to the executing of this method and there's no point in keeping them for any longer. But what about the heap memory? The heap memory doesn't get cleaned up automatically when a method is done, because the object on the heap might still be needed by another method, which is still on the stack. So the heap memory will be alive longer than the stack memory. In Java, you cannot manually clean up the heap memory. This cleaning of the heap memory is done by a JVM process, the garbage collector. The garbage collector frees up the heap memory so that it becomes available again to the application. This is not for all languages the case. For example, in C, you'll have to free up memory as a developer yourself. And that's working just fine, when it's done well though. Having the JVM do this with the garbage collection process actually eliminates a lot of common problems and mistakes by developers. First of all, the dangling pointer bugs can be avoided. This is when the developer did free up the memory, but the pointer is still pointing to the old place where a certain variable was stored. You can imagine that this can lead to unpredictable events, such as a pointer returning a surprise value, when the memory location has been reassigned to another value. Another common problem that Java developers don't run into is the bug of freeing up a memory region twice. This can especially be a problem when it has been reassigned to some other value that should not be cleaned up yet, and then it does get freed up for the second time, deleting the value that was still necessary. This is not a problem for Java developers. Thank you, garbage collector. And lastly, all sorts of memory leaks by not freeing up the memory that should be freed up cannot be reached anymore because the pointers are gone. So, for example, when I delete this pointer and the object is still on the heap, we can no longer access this object and we cannot free up this memory region. That's a problem. So, by now you must love this thing called garbage collector, right? But there are many options for the garbage collector out there. Making the wrong decision about what garbage collector to use can harm the performance of your application and even lead to out-of-memory errors. This is why it's very beneficial to understand the process of garbage collection well, so that you can use the best configurations for your application. Let's first see what is considered garbage in the next video. So, the garbage collector frees up memory on the heap. But how does it know what to collect? Once an object no longer has a reference to the stack, it becomes eligible for garbage collection. Phrased differently, the garbage collector considers it ready for removal. In this example, you can actually see the %p changing from a reference to the stack to the value null. And this means that our person object on the heap no longer has a reference to the stack. In other words, it's becoming eligible for garbage collection. And this is not only for direct connection to the stack, but also for indirect connection to the stack via other objects, for example. So we can see it happening here, because we have this pointer to the integer year of birth, but that's the only pointer is happening from the person object. The person object is no longer connected to the stack, and therefore it's also eligible for garbage collection. So that an object is ready for garbage collection doesn't mean it gets removed from the heap right away. It's up to the JVM to decide when the garbage collection process will take place. You cannot influence this with the Java code. You may have seen that you can actually suggest to Java to start the garbage collection with system.gc, but it doesn't guarantee anything. It's merely a suggestion to the JVM to perhaps start garbage collection. So when does an object get removed? Well, there are different implementations and strategies for the garbage collection, and you'll learn more on this later in the chapter. But they'll all consist of two types of steps, marking and sweeping. In the next video, we'll deal with the marking. So imagine we're having a heap full of objects. Let's leave out the Java garbage collector for a while here and try to think like garbage collectors ourselves. So how are we going to find out which objects don't have a connection to the stack? Well, here's the stack. And for now, for just a second, pause this video and pretend to be the garbage collector. How to find out which ones don't have a connection? Frankly, we cannot do this in one step. We'll first have to sort out which ones do have a connection to the stack. And if we have identified all the reference on the stack, we know which objects have a connection to the stack. Next, we're going to see what the references of these objects are, and also these objects have a reference to the stack, indirectly. We repeat this until we have checked all the nested references, and then we know what objects have a connection to the stack. And with that knowledge, we also know what objects don't have a connection to the stack, namely all the other objects. The garbage collector is doing something very similar. What it's doing exactly depends on the specific implementation of the garbage collector, but it always needs to do some sort of marking of the live object so that it knows that the unmarked objects can be removed. This marking can happen in different ways. A map with memory address keys and values of the state of the objects would, for example, be an approach that is common for marking objects. This map with the marking does take memory itself as well. In the olden days, there was actually a different approach. All objects would hold a counter, and this counter showed how often they were referenced. When a reference was removed, the counter would be decremented, and when a reference was added, the counter would be incremented. When the counter was 0, the object could be removed. At first, this probably sounds like a very clever and more efficient way than marking, but there was one problem: cyclic references. Two objects that hold a reference to each other but don't have a connection to the stack would never be removed because their counter would never get to 0. These so-called islands of isolation, object 8 and object 9 on this slide here, would live unnecessarily on the heap forever. And this is why the garbage collection happens with marking right now. The removing of the objects that are not marked happens in the next phase, sweeping. In the next video, we'll have a closer look at the sweeping phase. After the marking of the live objects, it's time to delete the leftover objects that were not marked. This deletion is called sweeping in the garbage collection slang. And of course, it wouldn't be fun if we only had one way of sweeping. Instead, we have three options for sweeping: normal sweeping, sweeping with compacting, and sweeping with copying. Let's start out normal. So let's look at this memory here. And say that these bits, they are not marked and so they can be deleted. This is what happens after deletion. It's the old memory, but with the available blocks of free space in between. So if we want to store a new bit, like this one, the JVM is going to have a look at the heap and is going to figure out that it can be stored over there, like this. But say we'd like to store a bit of a bigger one, then it cannot fit in between the gaps, so it can be stored at the end over there, like this. And say we want to store an even bigger value, and technically there would be enough space for this value, but it cannot fit at the end, so this will actually result in not enough space available and eventually an out-of-memory error. So this could have been avoided if we would have used the second option for sweeping with compacting. So here we have our memory again, and again these bits, they are not marked and thus will be swept. We don't just delete these bits and leave the gaps, but we'll apply compacting so that after compacting the memory looks like this. And if we then want to store a bigger value now, we do have memory block large enough available and we don't get the out-of-memory error. There's a very similar strategy to the sweeping with compacting available, and that is actually sweeping with copying. So here's a memory again, but this time we're having an extra piece of memory since we're going to copy. These are the bits that are not marked and thus can be removed, but instead of removing them and then compacting the memory, we're just going to be copying the marked elements to the other memory region and then delete the full block in the first memory region. You may think that this sweeping with compacting and sweeping with copying sounds a lot better than just sweeping without copying or compacting, so why choose the one or the other? Well, the key here is performance and memory usage. Clearly, the sweeping with copying might be ideal, but it's taking up more memory. And something similar is true for sweeping with compacting. It might be ideal, but it does require an extra step. We'll dive into the different implementations of the garbage collector that use or combine these strategies soon enough. Let's now first have a look at a very important concept we didn't discuss yet: the different generations on the heap memory. Java actually distinguishes different types of heap memory, and this is relevant for the garbage collection algorithms. Java splits up the heap memory, and so it can manage it in a more efficient way. We have the young generation and the old generation on heap. And even though it's technically non-heap memory, we also have one other section. And this used to be called the permanent generation, but since Java 8, this actually has been replaced by the meta space. So first, the young generation. The idea is that most Java objects don't need to live a long life, and that they will be part of the young generation only. This is the part of the memory where new objects are created, so it must support very fast allocation of memory. This young memory itself is actually split up into two parts, the Eden space and the survivor space. New objects are created in the Eden space, and as soon as a certain threshold is reached, the garbage collection starts and moves objects that are still alive to the survivor space, cleaning up the Eden space. When garbage collection for the survivor space comes by, objects that are still reachable in the young generation on the survivor space are moved to the old generation, and they are probably going to be there for a while. The others are being removed. The copying of the objects from the young generation to the old generation is called scavenging, and the collectors doing that are called scavengers as a result. So this old generation contains objects that have been scavenged from the young generation, and having survived this round of garbage collection is typically an indicator that the objects are going to be there for a while. This old generation is also called the tenured space. So let's have a look at this in action. We have our stack memory, we have 2 references on it still, and in our Eden space we have 5 objects. There's 2 live objects and 3 that could be removed. So when the garbage collection comes by, it's going to be copying the live objects to the survivor space, and then deleting all the elements in the Eden space that don't have a connection to the stack. Then, when the garbage collection comes by again, we see that some reference on the stack is lost and we only have 1 live object in the survivor space. When the garbage collection comes by, it's going to be moving the other reference to the old generation, and the one that doesn't have a connection to the stack is going to be deleted. And once more, the old generation is also called the tenured space. This tenured space typically requires a different strategy for garbage collection, since copying all the objects again without that many unreachable objects, since most of them are going to be living a long time, it's an expensive operation. So sometimes this approach is chosen nonetheless, since the copying does leave big blocks of memory which allows quicker allocation, and this can be an advantage depending on the specific application. But often this is not the chosen strategy for the old generation. So let's have a look at this relevant part of memory that was non-heap, that I said was called the meta space. Actually, if you're going to be looking this up, you'll find that it's very often still called the permanent generation or the perm gen. One of the differences between the permanent generation of before Java 8 and the meta space as of Java 8 is that the meta space handles allocation differently and that garbage collection is handled very differently as well. So what is this meta space for? This meta space is actually storing the class's metadata, such as the class structure, and also the methods of the classes, constants, annotations, and all sorts of optimizations are stored. So pretty much anything that's needed for the JVM to work with the Java classes, metadata pretty much. This meta space actually gets allocated when the classes are loaded. Loading classes means that the JVM prepares the runtime representation of a class, and when the class loader is unloaded, the bit of metaspace memory that was used by that class gets released. And this doesn't happen before all the classes loaded by that class loader are no longer needed. That might sound a bit vague, let's look at an example. So we're having some object of type O, and we're having a reference to this in our Eden space, which means that we'll also have the metadata of O in our meta space. Then, when we have another object of O, nothing needs to happen in the meta space because we do have the metadata of O already. But when we get an object of type P, we do need the metadata of type P as well. So then at some point, the references of our objects, they might actually get removed. So let's start with just removing one, the first one. So we lost one O reference. This does not influence the metadata on the metaspace, since we still have another O object and a P object. So the objects on the metaspace, they're still needed, and they're still alive. But what happens when we actually lose one more? So now we lost the other O reference, and that means that we no longer need the metadata of our O anymore. So when the garbage collection is going to come by and is going to delete the O objects from the heap, it can also then delete the object from the metaspace. So please be aware here that as long as the objects are still in the heap, even though they're not alive, we do need the metadata in the metaspace. And then now we only have some P left, so as soon as that reference gets lost, we would also be able to remove that from the metaspace. I actually already said that the metaspace works differently for garbage collection, and there's only two triggers that can actually start the garbage collection on the metaspace. The first one is when the metaspace gets allocated and it grows beyond the threshold of the JVM, it will try to free up memory first. This is a special threshold that we'll see later. The second trigger is when the metaspace runs out of memory. It will try to fix this by running garbage collection on the metaspace. So these are the only two events that will trigger garbage collection on the metaspace. The metaspace architecture consists of different layers itself as well, but that's beyond the scope of this course. We now have enough knowledge about the young and old generation and the metaspace to have a look at generational garbage collection in the next video. Imagine that you have a Java application running. In order to mark every live object, you'd have to pass the application completely. Marking is an expensive process for this reason. You may wonder right now, why does the application need to be parsed? Well, imagine that you have to check all the objects on the stack. There can actually be objects be created afterwards if you don't pass this application. And if that happens, these later created objects, they're not marked on the heap, and thus they will be eligible for garbage collection. While they're still needed and in use, they've been newly created. This is why you would have to pass the application. And as you can imagine, that would be very expensive and horrible for the performance of your application. This strategy for garbage collection is actually called Stop the World. The opposite of this is a concurrent collector that can run alongside the application. How this is working is using a very clever mechanism, and we'll see it in the next video. But for now, just know that there are alternatives out there. So, the generational garbage collector is not collecting the full memory at once, but for example, only going to be focusing on the young generation. This works well for applications in which most objects die young. This is typically done with a copy strategy. And the decision of when to promote objects from young to old is of major importance for the performance of your application here. I'm not saying there's a good choice or a bad choice, it truly depends on your applications. If you let the objects live in the young generation for a bit longer, it helps them to have died and never to make it to the old generation. But if you make this time too long, the young generation will take up a lot of space and can run out of memory. Also, if you let them in the young generation for too long, the promoting to the old generation of all the objects that have made, since it was very long, it takes really long as well. So making the right choice is critical here. These generational collectors typically use a so-called remembered set. Simply put, this remembered set keeps all the references from objects to the young generation via the old generation to the stack. And this helps the collector in that there is no scanning necessary. Else, the indirect reference to the stack via the old generation would be missed when garbage was collected to only the young generation. So this helps in that there is no scanning necessary of the old generation, since the references are in a remembered set. These generational collectors typically use a different strategy for the young and the old generation. So the young generation could be a Stop the World collector that copies the entire set of live objects to the old generation, and the old generation could use Mark Sweep Compact Collector, for example. Either Stop the World, Concurrent, or any of the other options that are out there. What options, you may wonder? Well, we'll look into the different implementations of the garbage collectors in the next video. The standard JVM has 5 types of garbage collectors. There are some other ones out there, such as IBM's and Azul's garbage collector. And what they'll do, you can quite easily understand after running these 5 built-in garbage collectors. So the 5 ones are the serial garbage collector, the parallel garbage collector, the concurrent mark and sweep garbage collector, the garbage first garbage collector, and the Z garbage collector. So let's just start with the first one. The serial garbage collector uses the mark and sweep for the young generation and the mark sweep compact for the old generation. This garbage collector is running on a single thread, and it's stop the world implemented, meaning that the rest of the application is frozen until the garbage collection is done doing a full cycle. It is fine for small programs, but due to the stop the world, it's not what is typically chosen for larger programs. Then we also have the parallel garbage collector, and it's using the mark and copy for the young generation, and also the mark sweep and compact for the old generation. Well, this might sound very familiar after having seen the serial garbage collector, but there's a difference here. It's not running on a single thread, but is running on multiple threads, splitting up the marking, copying, and compacting phase. It is still stop the world, but due to the multiple threads, the world needs to be stopped for a shorter amount of time. This is a fine option for a multi-core machine. On a single-core machine, you might as well use the serial garbage collector, due to the costs of managing the multiple threads on a single core. So it's not really processing it parallel on the single core machine anyways. So then we also have the concurrent mark sweep, which is actually an upgrade from the previous one, because it's still doing mark and copy, stop the world for the young generation, but for the old generation it's doing mark, sweep and compact, mostly concurrent. Concurrent is different from parallel since it doesn't require the application to stop. It's doing it concurrently next to the application. So it's not just pausing until it's done, but it's concurrent with the execution of the application and running on multiple threads. This means that the application is running at the same time, which makes it very, very different from parallel. But there's a downside here. This will only work when it's running on a system that supports this, because it's a bit heavier. So it's using the mark and copy with stop the world for the young generation, mostly concurrent mark and sweep for the old generation. And with mostly concurrent, we mean that it's preferring concurrent, but sometimes whenever it's necessary, it will use stop the world instead. So that sounds like quite an upgrade, but the garbage first garbage collector, introduced in Java 7, is even improvement for the CMS garbage collector. So what this one does is actually dividing the heap in small regions. And the garbage first collector is parallel, concurrent, and incrementally compacting. It aims for a very low pass of the application, and thanks to this division of the heap in the smaller regions, this is actually possible. So this is much smaller regions than just the young and the old generations. But these smaller bits of heap, they are actually marked with the specific memory region. So the garbage first keeps track of the amount of live and dead objects per memory segment, and the segments with the most dead objects are collected first, hence the name, garbage first collector. The compacting still needs to happen stop the world style, unfortunately, but these pauses can be shorter due to the smaller regions. The garbage collector is the best choice for machines with a high performance and a large memory space. It is also running on multiple threads and is using concurrent and stop the world processes. So, what about the Z garbage collector? The Z garbage collector is the newest kid on the block in this list, and it has production status since Java 15. The ZGC performs all the tough garbage collecting work concurrently without pausing for more than 10 milliseconds. So, the ZGC starts with the marking of the live objects, but it does so in a special way. It's not keeping a map, but it's using a phenomenon called reference coloring. It stores the reference state as the bits of the references themselves. So the ZGC therefore only works on 64-bit systems, since the references don't have enough bits to do this on the 32-bit systems. The ZGC also uses relocation to avoid the fragmented memory as a result of the garbage collecting. It does this process in parallel with the application, since it doesn't want to pass for more than 10 milliseconds. You can imagine that this is tough for an application. Imagine that we have a reference to a certain object, but in parallel to the executing application, this object got relocated. So if we try to access it using the old reference, we would be accessing the wrong memory location. This is solved with load barriers. They run whenever references from the heap is loaded. It checks the metadata to make sure that these bits of the reference are based on the result. It may or may not do some processing before retrieving the result. And this magic is called remapping. Also, the ZGC is running on multiple threads. These are the standard garbage collector implementations that you can choose from nowadays. The best garbage collector depends on the system and the application. Knowing if the garbage collection is performing well requires monitoring, which is what we'll be looking at in the next video. There are a few metrics relevant for garbage collection. The first one is the allocation rate. This is how fast your application is allocating objects in memory. The next one is the heap population. This is the amount of objects that's alive on the heap. Next is the mutation rate. This is how often references are updated in the memory. Another important one is how long the objects typically live. The one application may have mainly objects that die young, while another application has a fair amount of objects that need to live for a rather long time. For monitoring the performance of your garbage collector, mark time and compaction time are typically the most important. The mark time is how long the garbage collector needs to find all the live objects on the heap. And the compaction time is how long it takes the garbage collection to free up all the space and relocate the objects. The garbage collection cycle time is how long it takes the garbage collector to perform a full garbage collection round, meaning checking all the objects on the heap. The larger memory space available, the better the garbage collection can do its job. If there was unlimited memory, we wouldn't need garbage collection at all. For the copy and compact collector, it's necessary to have enough space available for copying and relocating, for example. If there's only a tiny bit of memory available, the copy collector would have to start with a very small part, free up memory so that it would copy a slightly larger portion next time, etc. When there's very little memory available, you'll see the CPU usage go up for garbage collection because it needs the tiny cycles a lot. Choosing the right amount of memory will improve the performance of your application as well. Let's monitor a garbage collection process. In order to monitor a garbage collection process, we need some sample code. And look at this code, it's horrible, but it's going to do the job. So what's happening here? I have an infinite loop, and in this infinite loop, I'm adding 1,000 elements to an array list. And when there are 1,002 elements on the list, I'm going to create a new array list. So all the elements on the list become eligible for garbage collection at that point. Then I set I back to 0, and so on and so on. It's an infinite loop. So I'm going to be starting this, and then I'm going to open a profiler so we can actually see this. So this has started. Let's move over to Visual VM. So here we have the example process, and I'm going to click on the monitor. And as you can see here, the memory on the heap is increasing and then it's decreasing again. So the garbage collection is doing its work. So how can I see that this is not too bad? Well, I'm looking at the heap size here, and I see that every time when the garbage collector has been there, it's going back to around the same memory level, meaning that the memory used is not constantly increasing a tiny bit over time. So that's a good sign. And then another one that's good is that the CPU usage is quite steady and not too high. I can do more in here, but we'll actually be showing that later. In the next chapter, we're going to have a look at the usage of JVM tuning to improve the usage of the memory by the JVM. Here we'll also see how we can tune the garbage collector. The Java virtual machine, better known as the JVM, can be configured to optimize the performance of the application. Why is that, you may wonder? Well, JVM provides the runtime environment for the application, so when that's one being changed, the application might actually perform better. All applications are different, and even though your application might be performing just fine, it could be performing even better with different JVM parameters. JVM tuning should typically be the last improvement step to your performance though. First, make sure that the code is optimized. JVM tuning is not just changing the parameters for the JVM and then sit back and watch your application improve. So, what is it? It's actually more like some educated trial and error. You determine what the requirements for the application are, and you select the JVM parameters that fit this. You're going to select JVM anti-parameters, and next you're going to do some checks and measure. And if either of these checks and measures fails, you're going to have a look at the application and requirements again and adjust the JVM parameters. These are the questions you should ask for tuning the JVM. First of all, is the memory functioning alright? And with memory, we do mean the heap memory over here. So if this is functioning alright, this means that there is the right amount of free heap available. Not too much and not too little either. Next, is the latency alright? Latency is the time it takes to perform an operation, and whether it's normal or not depends on the requirements. It's also called responsiveness, so how quickly the application responds to a certain stimulus. If the new JVM parameters made it worse, this is a problem. And the last question you should ask is the throughput normal? Throughput is the amount of work that can be done per chosen unit of time. High throughput typically means that the application requires more memory and that responsiveness might be decreased. Let's have a look at some of the options for tuning the heap size. So, alright, when we want to do JVM tuning, we kind of need to know what's going on in the JVM. So, how to get the metrics of what's going on in a JVM? There are actually multiple options. First of all, there's a bunch of command line tools for this. There's also all sorts of visualization tools, and there's some more complex profilers. Profilers will really get you some insights of what's actually going on inside the JVM by showing the JVM metrics. It's doing so monitoring the Java bytecode, and it's seeing how it's really operating at the JVM level. So, for the purpose of this course, we're going to be diving into the first two. So we're going to have a look at the command line tool, gstat, and we're going to be using Visual VM for visualization. So, first of all, gstat. What is this? Well, it's actually a JVM statistics monitoring tool, gstat. How to use it? On the command line, we use the command gstat. You have it already, that's the great news here. And then you have all sorts of output options. You can specify an interval and an amount of time you'd like to do this. So we're going to use the output option gc-util, garbage collection util, to see some things going on with the garbage collection. And we're going to do so using our example application again. So I'm going to be starting this application, and once I've done that, I need to find out the process ID of this application. And I could do so using code, but instead I'm going to be using my activity monitor. Alternatively, you can also use Visual VM, which is the one I'm going to be showing next. Or you can just use code to do this, but this is a bit too complex to go over right now. So I'm going to be running this example main. So here's the activity monitor, and I'm going to be looking for Java in here. And as you can see, I'm actually having two, and it is this one. So the PID is 58324. All right, let's not forget that. And then inside this terminal, I can actually use gstat. I'm going to go ahead, say gstat, and I'm going to be using it with gc-util. So I'm going to be adding gc-util over here. Then I'm going to be entering my PID 58324. And then I'm going to be saying that I actually want to see it at, well, let's just say half a second intervals, and I want to see 10 outputs of it. So every half a second, it's actually showing me a whole bunch of data. Don't worry, I'm going to be explaining this data right away. So here we can see it. We see the column names, and the column names are, for example, S0, which stands for the survivor space. And you also have the S1, which is also the survive space, but there's a difference actually. And this is the utilization as a percentage of the space current capacity. So we also have the E, the Eden space, O, the old space. Then we have M for the meta space. We have the young generation garbage collection events. We have the young generation garbage collection time. And next to that, we have the number of full garbage collection events, which was still 0 all the time. We also have the full garbage collection time, which is actually a very relevant metric, but we don't have any at this point just yet. And we also have the total garbage collection time, which is in the very last column. The other ones, they're not too important for this point. But here you can see all this data, and actually there's so many more options. If you want to know all the details for gstat, I can best recommend you to the Oracle documentation. Here you can find so many more options. So you see, for example, all the output options you're having, and all the things you can do with them. So for example, we use the gc-util new right now, but there's actually also a possibility to go ahead and see what's going on with the gc capacity. Alright, so that's gstat. What about Visual VM I told you about? Well, Visual VM, well, you may have guessed this is a visual tool. And it has a bunch of integrated command line statistic tools and some very lightweight profiling. So this is not going to be a deep dive profiling, but it's definitely enough to give us some quite idea of what's going on inside our application. And we can actually also inspect heap dumps with it. With heap dumps, we pretty much just mean a snapshot of the memory at a certain time. And this can be very useful when you want to know what's going on inside the memory and what's all stored in there. So here we're having Visual VM, and we can see the processes that are running on my computer. So I'm going to be clicking on this one, which is the one that's running the application that we just started. We also use gstat for this. So what am I seeing here? Well, this is just the overview. We can see what process ID is running on, the host, the main class, and some more details of the application. it's more interesting for us right now to actually go to monitor. And in monitor, we can see live what's going on in here. We see 4/4 of the screen pretty much. We see the CPU usage and the garbage collection activity in the left upper screen. In the right upper screen, we see the heap and metaspace usage. So right now we're looking at the heap, and we can see that our heap is looking very healthy. It's making nice ups and then goes all the way back down again when garbage collection kicks in. In the tab next to it, we can actually also see the metaspace. Then, in the left lower corner, we see the classes inside our application. We can see the total that are being loaded and the total that are being unloaded. Then, on the right of that, we can see the threads inside our application, which can actually be used for spotting deadlocks and live logs and all these sorts of events, but they're not relevant for our memory. Alright, so this is what we can do with the monitoring. What we can also do, we can trigger garbage collection here, which is quite cool. And we can also say that it should create a heap dump. So, for example, if I click on this heap dump right now, it's going to be creating a heap dump, which is a snapshot of the memory. And as you can see, we're having it right here. So what's going on with this heap dump? Well, we see some summary statistics here. We see the classes by number of instances, instances by size, and all sorts of details. But we could, for example, also dive into objects a bit more. For now, I'm not going to be going too much in depth here, but we can see, for example, how many of byte arrays are inside our application and how many of string. Also, we can go ahead and have a look at all the threads inside our application, but this is not too relevant for a memory, so I'm going to be leaving this here. So this is Visual VM, and you'll find yourself using this rather often when you want to know what's going on inside your memory real quick. So this Visual VM is actually the one that I'm going to be using most for the rest of this chapter, because this is going to be serving the purpose of showing you what's happening inside the memory. The heap size is where the objects of the Java application live. They're objects and free memory. The size of the heap influences garbage collection directly. A smaller heap size means that garbage collection will have to take place more often. If garbage collection needs to happen too often due to a too small heap size, this might influence the performance of the application. Depending on the system, this might be very unnecessary. You clearly cannot have more heap size than RAM, but when that's not a problem, the heap size can be increased. Another problem can occur when you set your heap size too big. If the heap size is too big, the GC will take unnecessarily long to do a full garbage collection cycle. The best heap size is in line with your application's needs. A fine rule of thumb is to have a GC under less of 5% of the execution time of your application. Alright, enough talking. Let's see how we can actually change the settings of the heap. So, here we're having the application again. It's still not a great application, but it's still perfectly fine for demonstrating how we can adjust the heap size. So let me first just start the Java example. There we go, it's a Java example, and it's going to run now. Let me move to Visual VM, and here we can see the example process. We can see underneath JVM arguments almost in the middle of the screen that there's no JVM arguments. And if we click on monitor, we can see the max size of the heap. It's around 8 GB. Let's start the application again, but this time with a much smaller maximum heap size. So how to do that? Well, I'm going to say Java again, but now I'm going to give a JVM argument. I'm going to say xmx, and then in here I can just specify the amount I would want. So for example, I can say 1024 megabytes. For megabytes, I just use the M. For gigabytes, go ahead and use the G. And then I specify the name of my application. There we go. I'm going to go back to Visual VM so you can see what has changed. So here's the new example process, and you can see that we have the JVM arguments xmx 1024 megabytes. So let's move over to the monitor, and you can see that our max has now been adjusted. If you're confused about this number not being 1024, etc., this is because of the conversion from megabytes to bytes. 1 megabyte is 1024 kilobytes, for example, and so on. So this is why we get this deviation in the number here. But you can see that our application is doing quite well. Garbage collection activity that's in the screen is fluctuating between 0.0 and 0.1. Well, that's outstanding actually, so nothing to complain here. But as you might guess, I'm going to see if I can make it perform worse, so you can actually see the difference in performance. So I'm going to kill this one again. And now I'm going to be starting it with just 16 megabytes. There we go. Moving back to Visual VM again. And you can see the new JVM argument And if I'm going to click on monitor, you can see that our max heap space is now really small. And you can see that our garbage collection activity is now 1.6, which is still pretty decent, but it's 16 times higher than the previous one. So clearly, the CPU has to work a whole lot harder right now. So here's how you can see how the heap size influences the CPU usage directly. There's actually more options that you can specify, and you probably won't have to do this very often, but just know that they exist. For example, if you would have to set the max for the young generation, you could go ahead and say -xx colon and then max new size, and then you'd have an equal sign, specify the amount, and then, for example, the megabyte again, the unit. And then in here, you go ahead and you put the name again. So this is how you can specify the max new size. And there's plenty of other options out there. For example, you could also say XX heap dump on out of memory error, which we will see later. Similarly, as to adjusting the heap size, we can also adjust the metaspace size. Let's have a look at how to do that in the next video. The max metaspace is not really defined by default. Once it reaches its limits, the JVM simply increases it. However, we can set a maximum size. We do so by adding an option to starting our application. Just say XX colon max metaspace size equals and then the max metaspace size. We can also set a threshold for garbage collection. Remember that there were only two triggers that could trigger the garbage collection of the metaspace. One of them was the threshold, which we can set, and the other one is when it runs out of memory without the garbage collection. Setting the maximum size or the threshold doesn't mean that it's actually going to be affecting the startup metaspace available. It just uses what it needs until it reaches the maximum. Then there's one last thing that you can adjust for the metaspace, and that's the minimum and maximum of free memory ratio. This can be useful if you plan on loading many classes dynamically and you may need some empty memory available to improve performance. Setting the maximum size for the metaspace can actually be very critical to your application. Migrating from Java 7 to Java 8 really was a disaster because of the changes in the permgen versus the metaspace, and not setting the maximum size could actually make applications have a very heavy memory footprint. Let's move over to IntelliJ and see how to adjust these variables. So again, I'm going to be using the very same application. And I would have to say Java and then specify the option. So for example, if I would want to set the max metaspace, I could say -xx and then go ahead say max metaspace size equals and then some sort of value. So I could make it very small. I could, for example, say that's only allowed to have 4 megabytes because I think 8 is enough, but 4 is going to be too little. And then I'm going to say example here. So let's see if we can break it. So it's starting now. Let's move over to Visual VM and inspect our process. Here we're having our process and the max metaspace size equals 4 megabytes. All right. So if I'm going to move over to monitor, you can actually see that the heap looks fine, but all of a sudden we don't see the CPU. And if I'm going to click on metaspace, you can see that this is all the size, the max unused. It's all around the 4 megabytes. So this is a problem. And actually, if we try to close this application, it's most likely going to break. So let me terminate this application, and then we get the out of memory occurred. So actually, it's not capable right now of closing, so we need to forcibly terminate the VM. So I'm just going to close this terminal, which will actually close the VM, but I'll also have to close the Java process. So I'm going to be terminating this. And then in the terminal, I'm just going to kill the process. And I know what PID it's running on. It's running on 85600. So let's just go ahead and then kill it over here. Kill 9 and then 85600. All right. Usually we don't need to do a lot for the metaspace, but if you need to restrict the usage of the application on your server, for example, this can definitely be the way to go to manage the resource that you're having. As I already mentioned, when you're migrating from Java 7 to Java 8, for example, you probably want to do this. But it's more common to tune the garbage collector. In the next video, we'll have a look at some of the options for tuning the garbage collector. The garbage collection process is an expensive one, and that means it's taking up a lot of CPU. As already mentioned, changing the heap size also changes the functioning of the garbage collection. Please keep that in mind as well. Before you start adjusting the settings of your garbage collector, you'll want to have a look at the memory. See which different types of spaces are filled, when this typically happens, etc. There are extremely many options for tuning the garbage collection, but we'll only have a look at a few. First of all, you can choose the type of the garbage collector, so for example the serial garbage collector or the concurrent mark sweep garbage collector. And per type of garbage collector, there's even more settings. I'll show you the official documentation where you can find everything, because this video is going to be way too long and you're going to be fast asleep by the end if I'm going to go over all of them here. But what is good to know, if you look at the heap, this is what the healthy heap looks like when the garbage collection is doing its job well. You can see that the memory usage is increasing, and then the garbage collection kicks in, memory usage decreases over time, and it decreases to the previous level. Then it increases again, and it decreases to the previous level. You don't see an increase of the base level of the memory, so to say, over time. Here's an example of an unhealthy heap. Here the garbage collection process is not working well. Actually, the garbage collection process is working well over here, but in this case there is a memory leak, which we'll learn more on later. But you can see that here, over time, the garbage collector is not doing its job effectively. It's actually not managing to get it back to the base level. Well, we can't blame the garbage collection here, because no setting of the garbage collection would have fixed this. But what you can often fix is when the execution time of the garbage collector gets too high. So when starting the JVM, you can specify what garbage collector to choose. For example, you can say use serial garbage collector, use parallel garbage collector, use the concurrent mark sweep garbage collector, the garbage first garbage collector, or DZ garbage collector. And depending on the ones you are choosing here, your application is going to be behaving differently, so please do keep that in mind. And know that for all these garbage collection choices, you'll actually have specific options. For example, for the parallel garbage collector, you can specify how many threads to use by adding the parallel GC threads option. There are so many more options. Before I'm going to show you a demo of how to use this, I would like to show you the official Oracle documentation first, so that you can have a look at all the options that are out there. So here we have the Oracle documentation, and it starts with the general tuning. But for example, if you want to know what's possible for the garbage first garbage collector, you can move over here. So here we have all the options for the garbage first garbage collector. And as you can see, there are quite a bit of them. They have the options and the default values here, and then the description of what it's actually doing. So for example, if you would want to know this for the concurrent mark sweep garbage collector, we would move here. And as you can see, there's this description, and in bold we see the options that we're having. So for example, we can use the use garbage collector overhead limit when we want to disable the feature where we actually stop the application with out of memory when we are spending 98% of our time on garbage collection. And so there are many more options in here, and all these garbage collectors, they have specific options. Alright, let's move over to our application again and see whether we can see the impact of using the serial garbage collector. So I'm going to be starting our application again, but this time I want to do so using the serial garbage collector. Say use serial garbage collector like this for our example class. And now I'm going to move to Visual VM. And we can see we're using the serial garbage collector. And then I'm going to move here. And you can actually see that this time the garbage collection activity is very, very low, which makes sense because it doesn't need to do a lot with this large heap size. But if I'm going to be decreasing the heap size now, you'll definitely see the impact. So let's kill the application and now also specify the max heap size. Let's just tease our application a bit and put it to, well, what shall we do? Let's go for the 16 megabytes again. And as you can see, we're using both arguments here, and we're going to be monitoring it. And as you can see, the garbage collecting activity is right now at 0.6%. Alright, let's have a look at what happens if we use the parallel garbage collector here. So I'm going to be updating this to the parallel one. Open our new process, and we can see we're using the parallel garbage collector, and I'm going to be monitoring this. And funny enough, you can see right now that it actually has a larger garbage collection activity. And this is not too weird, because it's actually a very simple process. So the cost of organizing this in parallel is higher than doing it serial, which is quite funny. Let's see what happens if we try to use the first garbage collector. So I'm going to be updating this to the G1 garbage collector, so we don't need to use word here. We do need to use word there. So we can see we have the new options right now. And as you can see, our garbage collection activity is quite high. It's compared to the parallel one. So the winner so far is actually the serial garbage collector. Truth be told, we're only looking at the garbage collection activity here. And it's actually very possible that when we're not only looking at garbage collection activity, but we're also going to look at, for example, the latency of our application, the throughput, that the other options are actually better. So this is why it's very important to always measure everything, so that you can see the impact of which garbage collector you're using. Because as you can see so far, it does definitely impact your application. In the next chapter, we're going to have a look at memory leaks. Let's talk about one of the biggest problems that can come from poor memory management: memory leaks. Memory leaks are the accumulation of objects on a memory that are actually no longer needed. Objects are created, but the memory doesn't get freed when they are no longer needed. The reasons for this may vary, and the number of objects on the memory will just keep on increasing. Sometimes this goes very slowly, but it can also go quite fast. Eventually, the memory gets so full that it slows down the application, and ultimately it leads to a crash. And when the memory is so full and there is no memory anymore, we'll encounter an out-of-memory error. This kills the application. Memory leaks are a serious problem. Even nowadays, when most applications are developed in a high-level language with memory management, for example, by the JVM in Java, there is still plenty of opportunities to create memory leaks in your code. And this can also happen on super fast servers. Why? Well, the RAM is a limited resource, even on the best servers, and a limited resource can get full. If you host your application in the cloud, you may think right now, then we'll just scale up and we won't run out of memory. Well, depending on the settings, that might be right, but it will at least result in unnecessarily high cloud costs, because you'll need to run an instance that is bigger than it should be due to the memory leaks. Crashed applications are unavailable applications, but also when it's very slowed down, it might be unavailable. There's no need to tell that unavailable applications are not good for keeping, let alone growing, your users of your application. So, enough reasons to be spotting, solving and avoiding memory leaks. Let's see in the next video how we can detect memory leaks. Memory leaks don't seldomly exist unsolved. Just restart your application and you're good to go for another X number of days. Clearly, this is no one's preferred option, but if you don't have a clue what's going on, or perhaps you don't have the time to find out what's going on, it might just be that. By the way, a slow application does not always mean a memory leak. So, how to spot memory leaks if that's not it? Can you tell by just using the application? Well, no. The slowing down of the application is often an indication of a memory leak, but this slower application is definitely not guaranteed to be caused by a memory leak. In order to be sure, we'll need to do some monitoring. The metrics we'll have to look at is the heap memory size and the portion of that will be full. And we can actually also inspect the garbage collection activity, and we can have a look at the heap dump. I have created an application that contains a memory leak. Let's have a look. So here is the example that actually contains a memory leak. Maybe you're really quick to spot it, but if you don't worry. We're going to see what's happening first. So we have a list of persons, and person is a new object I've made. It's over here. This is the person class, and it just contains a name. It also has a constructor that's going to be setting the name. All right. So what we're doing, we're infinitely adding a person to our list, a new person. Why infinitely, you may wonder? Well, this time we're not incrementing I at the end of our loop. All right, let's run this application. There's actually multiple ways to run the application. We could just press the play button, but we can actually also start it with the command line. And there's an advantage here, because if we start with the command line, we can create a heap dump. So let's just go ahead and do exactly that. So I'm going to say java-xx : heap dump on out of memory error. All right. And then I also want to specify the path for a heap dump. If we don't, it's going to be using some default path, but I don't want it right now. I actually want my heap dump to be in heap dump path equals, and I'm just going to put it in users, my name, and then HD, heap dump. I think that's a fine place to store in heap dump. And I'm also going to say example OOM because this is the class that I want to be running here. All right, let's run this one and move over to Visual VM. So here we're having our process, and as you can see, the heap is getting quite full already. The CPU is busy, quite busy actually, and it's working really hard to try and avoid this heap dump here. You can also see the garbage collection activity sometimes increasing, and not long from now, it's going to actually crash with an out of memory error, hence the OOM, it stands for out of memory. And there we have it. It crashed. All right, so it has made a heap dump, but this can actually take quite a while because the heap dump is going to be quite big. So here's the folder. This is not too interesting. I'm just showing you it's in here. And what is striking is that the size of this document is huge. So how to open a heap dump? It's a weird extension, right? Well, you can definitely open this in Visual VM. You can open it in some of the IDEs as well. But if you try to open this with TextEdit, for example, you will see a lot of text that you can actually read, but it's impossible to make sense of this. So I'm going to go for Visual VM to open this one up. And actually, opening the heap dump will help you to see what's actually a heap dump. It's literally a dump of whatever is in the heap. So all the objects, they're in the heap dump. So I'm in Visual VM and I'm going to say file load, and I'm going to be selecting my heap dump over here and I'm going to be opening it. And this can actually take quite a while because, as you just saw, it's a huge file. All right, so let's first look at what we can actually see in Visual VM about the memory crashing. So we started our application and we could see the memory increase, and we could actually also see the CPU usage being quite high. And after the garbage collection actually set in here, we could see that when this was done, the CPU dropped again, and then it would start to increase again. And the garbage collection activity was, well, it's not too bad, but it is quite high, especially if you see nothing happening on the heap in terms of the memory being decreased. But as you can see, this memory is not very typical for a healthy application. You can see it has a baseline, but the baseline is incredibly high. So this is quite worrying, and even though you see it drop at some point, you actually also see it increase again quite soon, and then it cannot actually do garbage collection again after that. So you may wonder, how is it even possible that it is managing to collect some of the items? Because, well, we didn't really have anything that was eligible for garbage collection inside our application. Well, there's tons of strings and stuff in Java that are being loaded by a JVM that can actually be removed later. So this can actually be done when the garbage collector really needs to be removing something and there's nothing else that can be removed. Then this is typically what the JVM would be doing. You can also see it in the left bottom graph, which is actually the total loaded classes. You see that there's a whole bunch of classes loaded and only a few unloaded. We can also go ahead and have a look at the meta space, but this one is quite constant since we're not doing a lot over here. So to sum up, how can I see here that something's wrong with memory? Well, it's not too obvious in this case, but there are some very, very clear indications. First of all, the memory heap usage, the blue part, is quite high, and the line doesn't have anything that's dipping. So it has a very obvious dip, but this is only the initial garbage collection cycle, and even though I can see that the garbage collection activity is quite constant, there's nothing else happening to the heap, which is typically an indication of something being wrong. Well, clearly in a different application there might be more going on, and there could still be reasons that the garbage collection can actually be removing something. So there you actually see more dips in the used heap. But what you'll see in these types of applications, it's very much like one of the previous slides in the very first chapter of this course, where you could see that this has these kind of saw teeth, which was just going up and down, but then it wasn't going down as much as it went up. So it would just have a higher base level every time after it went down. And this is very typical look for the used heap of an application that has a memory leak. Alright, so here's our heap dump. And, well, what can we see here? We are looking at the summary right now. We can see this on the top, on the left, it says heap dump, and underneath it says summary with a drop down. Actually, not all data is available yet. What's relevant for us to see? First of all, we can see the classes by number of instances. And this is already quite striking, because in this case it's super obvious, and we can see what went wrong. We have really a lot of the person instances in there. And On the right of that, we see the classes by size of instances, and also there the person object is very dominant. So this is a very clear indication to us that this is actually the problem with our application. Well, we can actually see more, because sometimes you would like to see more. So, for example, we can have a look at the out-of-memory thread, so we can see what happened. And in this case, we can see that it happened with the adding to the array list. And there's something else that we can actually see. We can also check out the objects, which is also often very relevant. So here we have the summary, and then beneath there we have the objects. And we can sort them in different ways, but we can, for example, also see what they have references to. So for example, if I open this one and just grab any person object here, and I'm going to be asking what this has references to, I can actually see what's holding a reference to this object. So why does this still need to be in my application? And as I already said, this is very big, so heap times navigating is typically very slow. You can see the computing in the right lower corner. Alright, so here we can see the object that's holding our reference. And as you can see, it's element data in the Java util array list. This is giving us some great clues as to where the problem is. Alright, so we can now detect memory leaks. That's great, but it would be even better if we'd know how to solve them after finding them, or actually even better, how to avoid them and make sure that they don't happen, which is exactly what we're going to be doing in the next video. Avoiding and solving memory leaks is not as easy as it may sound. The first step for solving them is the hardest, and we just saw how to do it. Find the problem. This is really the most important part of solving memory leaks. Next, it's very important to realize how memory leaks are created in Java. Objects hold unnecessary connections to the stack. If you can avoid this from happening, you can actually avoid memory leaks altogether. And once you have found the problem, it's actually time to improve the code. There's usually no need for complicated JVM tuning. You'll just have to look critically at your code and fix the problems in your code. Let's have a look at how to fix it for our example. And this is actually very easy because, well, I already told you what was wrong. We got this out of memory because we actually got stuck in an infinite loop and we could never get out, and we were just adding person objects to the list and adding person objects to the list. So when will we actually get out of this loop? Well, we can either decide to break out of the loop, which will probably solve the memory problem, but what we can also do is just create a new array list every now and then. And this will actually be enough for Java to start cleaning up the heap. Because when we have a new array list and it's stored in the old variable that was holding the reference, there's no longer a need to keep the old array list or all the objects on it. So just making sure that I gets incremented so that it reaches over 1,000 and then a new array list is being created. This will already solve the problem. Let me show this to you, but please mind this is running forever, so I cannot show that it's never going to be causing memory leak, but at least you can see the healthy heap behavior. So let me open this one. And I'm going to be monitoring this. And as you can see, it's going up and then it's going back down again. And this looks so much better looking at this. Because as you can see, the heap size is increasing and then it's decreasing again with the garbage collection activity. Also, you can see that the garbage collection activity is so much lower compared to when we had the out of memory error. Because then it was around 3.5% and now it's on average 0%. So this is pretty good. So this is what it looks like in a healthy state. So here are some things that can help to solve the memory leak. First of all, set the object to null in certain specific situations, such as what we just saw. If we would make sure that the original list is null, then there's no reference anymore, and then in that case it's ready for garbage collection. Also, make sure to close resources such as streams and connections, because keeping these resources open is holding a lot of unnecessary objects on the heap. Same goes for string concatenation. This is typically something you don't want to do because string concatenation is creating all these new string objects. So it's much better to use string builder instead, where you need to modify strings a lot. Also be careful with static collections holding objects. This is sometimes done, for example, when you don't have access to a database and you just want to write a script that's holding objects for a while. And by making it a static collection, all the instances of the class are sharing this collection, so it can be quite convenient. Please be very careful with this, because this can very easily lead to an out-of-memory error when it's not managed well in the code. Also, and this is more detailed already, but it's very important to override the hash code and equals, especially when you add custom objects to hash sets. So what's going on there is that if you don't override hash code and equals for your custom objects, such as we had with my person object that I just created, I did not override them. It's going to be using the default ones, and this can get very ugly when you override it to hash sets because it can get lost and it's going to be very hard to actually make the different piles of the object, so to say. And this can actually also lead to out-of-memory errors. But still, mistakes happen, so the key thing to take away is that you make sure that you monitor your application so that you can spot problems and solve them before anyone else notices. Congrats, you've done it! You've worked your way through some rather complex memory management topics. Next topics that would be very interesting for you would be logging, but also monitoring, and of course testing, and also other advanced Java topics might be interesting, such as design patterns and concurrency. Here are some courses that I've selected for you that would be great as a follow-up. First of all, the Java concurrency troubleshooting, latency and throughput, but also the monitoring and logging course, which will tell you more about how to monitor and log an application. Also, parallel and concurrent programming with Java would be very interesting. And of course, advanced Java programming is always a good one to take because it will take your Java skills to the next level. Then, if your Java is already really good and you want to know more about the design patterns, advanced design patterns, design principles might also be good for you. And finally, learning Apache Tomcat can definitely be interesting whenever you need to do some management of your Java applications. Thank you so much for taking this course.